Question number one, we have intersecting chords, and notice how the measurements are on the segments. So we're talking about segment lengths. We're not talking about arcs or angle measurements. Since we're talking about the segment lengths of inside segments inside the circle, intersecting chords, we're going to use our theorem, part times part of one chord equals to part times part of the other chord. So here's one chord, and here's the other. And the part begins where they intersect. So it's not at the center of the circle if there is one, it's where the chords intersect. So let's do the red chord first. So the two parts are 10 and 6. And then the blue chord, the two parts are 5 and x. So we have 60 is equal to 5x. And then if we divide, we have 12 as our x value. For number 2, inscribed means that it's inside the triangle and it's touching at one point on each of the sides of the triangle. Remember, if we have two tangents to the circle that come out of the same outside point, the same external point, they're congruent. So DC and CE come out of the same outside point, so they're congruent. And I'm just going to do colors instead of congruence marks to make it easier to see. DA and AE come out of the same outside point, so they're congruent. And EB and FB come out of the same outside point, so they're congruent. Two tangents to a circle from the same outside point are congruent to each other. They also tell us in the question that AF, FB, and 5 are all the same as each other. So AF and FB are equal to each other. So I'm going to make them the same color. But EB is also congruent to FB because they're tangents to the circle coming out of the same outside point. So I'll just update the color here so that we can see that all 4 of these segments are actually all congruent to each other. And it does tell us that these segments are all 5. They do also tell us that DC is 7, making CE 7. And all we have to do now is add up the measurements to find the perimeter of the triangle. So 8, 9, 10, 11, 12, 12, 10, 34 is our total perimeter. Over here, we have a tangent to the circle and a secant to the circle. These are outside segments. I don't know if I'm going to be needing to use my theorem for segment lengths for outside segments or for arcs and angles of outside segments, so the outside angle theorem. I got to read the question and see what information they give me and what I'm looking for. They tell us that PB is 9 and that BC is 16. So already I see we have information about segment lengths. And we need to find the length of PA. So we're finding a segment length. So we're going to be using our theorem for lengths of outside segments. And that is whole times outside of one segment equals to whole times outside of the other segment. So let's start with the tangent. The whole tangent is x, it's what we're looking for. And the outside part is also x, because the whole tangent is completely outside the circle. The whole secant is 16 plus 9, which is 25. And the outside part is 9. So we have x squared is equal to 25 times 9. I'm going to need a calculator for this. 25 times 9, 225. And then when we take the square root of both sides, we have x is 15. And x represents the length of PA, so the length of PA is 15. This diagram looks very similar to the previous one, but from reading the question, I already see it's different because it's not telling me the length of parts of the secant or the whole secant. It's telling me arc measurements and angle measurements. And it's actually asking us to find the measurement of an arc. Since this is dealing with arcs and angles rather than segment lengths, we're going to be using a different theorem than we used here. This was the theorem for outside segment lengths. So over here, let me mark my diagram and then I'll write down the theorem that we're going to be using. So arc QT is 140. And remember, when there's two possible arcs that are named QT, it's the shortest. So it's not this way around, it's this way around. And angle P, the outside angle, is 40 degrees. What is the measurement of arc RS? So what we're going to be using here is our theorem for arcs and angles of outside segments. And that is that let me be consistent with the colors here, sorry. That the outside angle equals to half the difference of big intercepted arc minus small intercepted arc. In order to see what the intercepted arc is for the outside angle that you're looking for, take the rays of the outside angle, so the rays that are stemming from the vertex, highlight them. And notice how inside my highlighted rays, we have this arc that it's touching, right, touching the rays. And we also have this arc that's touching the rays. So these are the intercepted arcs here for these two secants that are forming outside angle P. So now all we have to do is plug in 40 is equal to 1/2. The big intercepted arc is 140. And the small intercepted arc is what we're looking for, it's x. Multiplying both sides by 2 in order to get rid of the 1/2. I have 80 equals to 140 minus x. I'm going to subtract 140 from both sides. And that's negative 60. And then dividing by negative 1, we have x is equal to 60. And that represents the arc that we're looking for. So the measurement of arc RS is 60 degrees. In this diagram over here, we're told that AP is tangent to circle O at point A. When you have the name of a circle, circles are named for its center. So that tells us that the center of this circle is O, which tells us that OA is a radius of the circle. We do know that when a radius and the tangent meet, they're perpendicular, meaning that they form a 90-degree angle. So we have a right triangle here. We're looking for the length of AP. So we're looking for the length of this side of the right triangle. Remember also that all radii of a circle are congruent. And from O to B, this is a radius. And so is from O to A. So these are the same. And if you add up both pieces to get the full side OP, you have 25. And now it should be obvious that you can use the Pythagorean theorem to find the side that you're looking for. Just be careful when you're using a squared plus b squared equals to c squared, that your hypotenuse needs to go in for c. And you already have your hypotenuse. Your hypotenuse is 25. It doesn't matter the order for a squared or b squared. It's just one you're looking for and one you already have. It doesn't matter if I put a or b, the order doesn't matter. "25 squared is too big of a number for me. "625. Let's subtract 49. Oops. And now let's take the square root of 576 to see what we get. And that's 24. Notice we have outside segments once again. So I'm going to read the question and see what theorem I'm going to be using. I already see arcs, and we're finding the measurement of the outside angle. So I already know it's going to be the outside angle is half the difference of the intercepted arcs. The arc CD is 70, arc AB is 20, and we're looking for outside angle P. So once again, the outside angle is half the difference of big intercepted arc minus little intercepted arc. So big arc minus small arc. If you follow the rays, you'll see that this arc touches the rays, as does this arc. So that's the small intercepted arc and the big intercepted arc. So the outside angle equals to half of 70 minus 20, and that is 25. For this one over here, we have intersecting chords, but we're not going to use part times part equals part times part like we did before. And the reason for that is it's not asking us to find segment lengths. If you read the question, it tells us that arc CD is 46 degrees, arc DB is 102 degrees, and we're looking for the measure of angle CFE. So we are dealing with arcs and angles here, not with segment lengths. So when you're talking about arcs and angles with inside segments, you're going to use a very similar theorem to the arcs and angles with outside angles, except instead of half the difference, it's going to be half the sum of the arcs. So I'll just call it vertical angle, because that's what's created by the intersecting chords, equals to half arc 1 plus arc 2. Sorry for the mess there on the screen. So let's see what I can do here. I need X, but in order to directly solve for X, I need these arcs that are the vertical angles are opening up to. I can get it. I already know this is 46. DAE is for short diameter. They tell us that. And it says circle A, so A is the center of the circle. So from D to E, that would be 180. So if I do 180 minus 46, then I'll get what that arc needs to be. 134 degrees. Oops. So now I can directly solve for the vertical angles that I'm looking for. So the vertical angle is equal to half of the 134 arc plus the 102 arc. So let me do that in my calculator. 134 plus 102. 118. Perfect. This is a review from the previous test, but this kind of question is going to be on this test as well. We do need to know how to do it. First step is to group the x and the y terms together. So I am going to have to rearrange across the equal sign. Remember that if you move something over the equal sign, the sign changes because you use inverse operations to move it. For example, if I wanted to take this negative y squared and move it to the other side, I would be adding it to both sides, and that's why the sign would change. So just remember, when you move things over the equal sign, just a little review from algebra, the sign changes. So x squared is good. I'm going to give myself more space. X squared is good. 4x needs to come over to the other side, so that's going to become a negative 4x. And then my box. And then negative y squared needs to come over to the other side, so that's going to become a positive y squared. 6y is already on the left. I'm just moving everything I need over to the left. And the constant 12 is already where it needs to be by itself now on one side of the equal sign. I didn't show up all the steps for rearranging, because I think we can handle that. That is just moving across an equal sign from algebra 1. Okay, so now I'm going to do my b over 2 squared. So negative 4 over 2 squared for my x terms. Negative 2 squared, and that's 4. And then I can just really quickly factor this. The b over 2 before you squared it is what this is going to factor. Okay, now I'm going to do my b over 2 for my y terms. I'm just going to do it over here. 6 over 2 squared. 3 squared, it's 9. And I can just really quickly factor this as well. It's going to factor to the b over 2 before you squared it, which is plus 3. Let's really quickly just clean up the side. 10, 11, 12, 13, plus 12, 25. So the center of the circle would be 2, negative 3. Remember, when you pull out the center from the equation has a built-in negative, because the equation is x minus h squared plus y minus k squared equals to r squared. So there's already that built-in negative in the circle equation. So when you're identifying the center from the equation, just recognize that this had to be a 2, because in the equation with the built-in negative, we saw minus 2, and this had to be a negative 3, because in the original equation, there was that built-in negative, so that had to be a negative to turn into a positive. And then this is r squared. So that means the radius is radical 25, which is simply just 5. Over here, chords AB and CD are parallel, and that means that the arcs between them that they intercept are congruent. If AB is 104, arc AB, and arc CD is 168, what is the measurement of arc BD? So let's figure this out. We know that the whole way around the circle is 360 degrees. Let me add up what we have so far, 168 and 104. Let me get rid of that. So 168 plus 104. and that's 272. And then subtracting that from 360, oops, to see what's left on our circle is 88. And then we have two equal parts created by the parallel chords. So that would be 44. Okay, let me zoom this out so that you could see it better. Okay, perfect. Using a compass and a straight edge, construct a hexagon. I just want to point out that the hexagon and the equilateral triangle construction are the same thing. What I'm going to do is, actually, I'll do it with my straight edge first. That's better. I'll just connect, and mine is not going to be perfect on the computer. The computer compass is not good. It's going to make a radius. And that way I can measure. Put a little arc to show I measured, even though you can't really see it. And I'm going to keep that measurement the whole time of the radius. I'm going to go over there. And then I'm going to use that same measurement, and I'm going to intersect the circle. Then I'm going to go over to that point, and I'm going to use the same measurement and intersect the circle. And then I'm going to go over to that point, and I'm going to use the same measurement and intersect the circle. And then I'm going to go over to that point, and using the same measurement, I'm going to intersect the circle. And then that point, same thing. And then that point, same thing. And mine actually was really accurate because it should end up going back to the point that you started at. We have 6 of them. If you wanted to make an equilateral triangle, you would connect every other point. But since we wanted to make a hexagon, we're going to connect all 6 points. I also am going to label it just like the question says, else I'm not going to be able to know what it's talking about. It doesn't matter where you start labeling the points. You'll get the same thing even if yours looks slightly different. Okay, let me use my straight edge. I'm going to get a different color. And then make my hexagon. By connecting all those points together. Remember, for equilateral triangle, it's every other point. And now I'm going to do the second part. If chords FB, so here is FB, and FC are drawn, which type of triangle, according to its angles, would triangle FBCB? So according to its angles does not mean isosceles, equilateral, or scalene, that's sides. Isosceles is 2 equal sides, equilateral is 3 equal sides, scalene is no equal sides. According to its angles means acute, obtuse, or right. And if you take a look over here at angle BFC, that is outlined in blue by the connecting the chords. Notice how this is an inscribed angle of the circle, and I'll just darken it a little bit so you can see it. It's an inscribed angle of the circle. So is this one over here, and that's going to be the more helpful one. So let me try that outline that better. This is an inscribed angle, and remember, inscribed angles are half the measurement of their intercepted arc. Following this goes to F, and following this ray goes to C. So the intercepted arc for this inscribed angle is the diameter, is half a circle, is a semicircle, which is 180 degrees. So that means this is 90 degrees. So the answer would be this is a right triangle. And I'm going to write this down so that you can have the explanation as well, because it's important. Right triangle and inscribed inscribed angle that intercepts a, I'm just going to use semicircle for half circle. That's like the correct term, is a right angle. And there we go. Now we have a fill in the blank proof, so I'll leave it zoomed out. This one's kind of hard, and that's why the Regents exam gave it as fill in the blank. The one that you're having on the test uses the same ideas, but it's a little bit easier, and it's not fill in the blank because it wasn't given as a fill in the blank proof on the Regents exam. When they give fill in the blank proofs, it's a reason why. It's because it would be extremely, extremely difficult for people to fill in without it. Sorry. So let's look at our proof statement. It looks a little complicated, but what we're actually proving, because RS squared is RS times RS, right? So what we're actually proving is a product. And we know that we have 3 steps for proving a product. Number 1, we're going to prove triangles similar. Number 2, we're going to prove a proportion to be true using the corresponding sides that are in the proof statement that we need to get to. And then finally, we can prove the product because you cross multiply a proportion to get the product. So those are our 3 steps. So now that we know where we're headed to and what we're doing here, I can automatically fill in 8 and 9 without knowing anything and get myself 2 points on this fill in the blank proof on the Regents exam. Sorry. Corresponding sides of similar triangles are proportional in a proportion. The product of the means equals the product of the extremes. There we go. Oh, and I also know one more. In 2-column proofs, 99% of the time, how do we prove triangles similar? AA. Wow. All of that done already. Keep that in mind on the test. If you have to prove triangles similar, prove a product, you know the last 3 reasons. Automatically, you know it. It's the same every time. Okay, now let's go through the rest of it from the beginning. And since this is a fill in the blank proof, it did tell us which triangles we need to prove similar. Triangle RST and triangle RAS. So I'm going to start by highlighting those because if I don't know what triangles I'm focusing on, I can't do anything. So always identify which triangles you're focusing on, highlight them, and that way you know that you're looking for the congruent angle pairs between those 2 triangles. Well, RST is the whole big triangle. So you might have been confused. You might have thought that you were proving the 2 smaller triangles similar. And RAS. Okay, so the big green one and the still large but smaller red one. Okay. They're telling us that RS is perpendicular to ST. ST, or TS, is a tangent to the circle, and SR is the diameter. A tangent line to a circle is perpendicular to the diameter or to the radius. Either one works. And from that, we can conclude that angle RST, so that's in the big triangle, it's this full angle, is a right angle. And they give that to us, perpendicular lines form right angles. And then we need to determine why angle RAS is a right angle. So they're telling us that it is a right angle, but we need to figure out why. And notice how that's an inscribed angle that intercepts a semicircle. It opens up to the diameter, half of the circle, 180 degrees, making this 90. So, an inscribed angle that intercepts a semicircle is a right angle. And then now it's stating that those two right angles are congruent to each other. We all know this. All right angles are congruent. And now they're giving us that the other pair of angles is congruent by reflexive property. So notice how the small triangle is inside of the big triangle. Anytime you have one triangle inside another, or you have overlapping triangles, there's going to be something that they share, either a shared side or a shared angle. If you took the two triangles and drew them separately, you'll see that they both have angle R in common. They both have the letter R. So I highly recommend drawing separately. I can do that over here so you could see it better also. Okay, so this is R, AS, so that we could be sure as to why. Because remember, on the test, you're going to use the same ideas, but you need to write your own proof. So now that they're separated, notice that they do have R in common. You might be wondering, okay, they also have S in common, right? But if you take a look at S in both of the triangles, in the red one, angle S is this, but in the green one, angle S is the whole right angle. So they're not actually the same, even though they have the same letter in the triangles. So we can always double check with the diagram, because this one's definitely smaller than this one. But angle R is exactly the same in both of the triangles if we double check with the diagram. And there we have our AA, which makes our proportion true, which makes our product true.